In this video, I want to discuss who actually calculated the number pi. The number pi as we know it today, as 3.1415 and so on, is a never-ending number that we call an irrational number. And it's used in a lot of different applications in maths and engineering and science, but who was actually first credited for discovering this number, and how was it found? So that's what I want to talk about today. And I'm going to start by looking at the area of this particular circle. This is what we call a unit circle, and it has a radius of 1. And hopefully if we can remember from high school that the area of a circle is pi r squared. The unit circle has a radius of 1, so we can sub that into the equation, and we get pi times 1 squared, which is simply 1, and we get the area as being pi. So the space inside this circle has an area of pi. And that might not seem so strange to us, but back in the day, in the times of the ancient Greeks, this was very perplexing. There was a point where they hadn't discovered the identity of an irrational number. They knew about whole numbers and integers, and even rational numbers, where a number could be expressed as a ratio of two integers. But the idea of an irrational number or a never-ending number, a number that could not be written as a ratio, was still out of their reach. So if we go back in time to the ancient Greeks, we start by looking at the discoveries that came out of the Pythagorean school. And probably the most important one was the Pythagoras Theorem, which then changed the way they viewed the whole number system. And we're going to look at a particular strategy called the Method of Exhaustion, which was the method Archimedes actually used to discover pi. So let's look at this particular triangle here. This is a right angle triangle, which I should have a little box in the corner to tell us that. And it's also an isosceles as well, with the sides 1 and 1. So if we wanted to find the value of the question mark, I'm sure we can all use Pythagoras Theorem, which states that the sum of the square of the two shorter sides, most commonly referred to as A and B, is equal to the square of the longer side of the triangle C, the hypotenuse. So substituting in, we have 1 squared plus 1 squared gives us our question mark squared. Or in other words, what number can I possibly multiply by itself and get an answer of 2? And most of us, I'm sure, can just happily say that this must be the square root of 2. But to a member of the Pythagorean school, they had to stop and think, because square roots and irrational numbers, that wasn't a thing back in the day, and they had to really think about what number could possibly give me, when I multiply by itself, give me an answer of 2. So they couldn't think of it. And so they extended, okay, let's see if we can extend the sides of the triangle, maybe we can get close to an answer. So if we consider a triangle with the sides 5 and 5, we can very easily again use Pythagoras' theorem, 5 squared plus 5 squared. So 25 plus 25, which gives us 50. Now we know that that's very, very close to 7 squared. 7 squared is 49. So the best that they could conclude was there was a number that was just a little bit bigger than 7. All right, so 7 squared being 49, 50 is very close to the square of 7. Again, extending it even more, we can have two sides of 12 and 12. 12 squared plus 12 squared gives us 288. And we know that that is very, very close to 17 squared, which gives us 289. So the hypotenuse of this triangle must be just a little bit shorter than 17. And really, if we continue this line of thinking and form a proof of what we call a proof of contradiction, a member of the Pythagorean school, whose name was actually Hippasus, arrived at this result and was able to prove it, that there is no way to measure the isosceles right triangle so that every single side is a whole number. And therefore, the discovery of an irrational number was born. And now, back in the day, this was actually quite scandalous. Remember that these people were often, the members of the Pythagorean school were often ostracized for their peculiar ways of thinking. And Hippasus was actually drowned not soon after that discovery. So there's a story in there and a proof of how he discovered the existence of irrational numbers, but I'll let you go research that, or I might talk about it in another video. But you are welcome to go read up on Hippasus and his proof of irrational numbers. Now, let's continue on with the method of exhaustion that we talked about earlier. So here we have again, we start with the unit circle, but this time I'm going to draw a square inside it. And this square is called an inscribed square. Inside the circle with a radius of 1, what is the area of this square? So hopefully we can see that the area of this square is actually just 4 lots of those triangles, which we saw earlier on. We can see the right angle there. And so the area of each triangle, we can recall as being half times the base times the height. So the base and the height are both 1, so we have half times 1 times 1, leaving us with 0.5. And as we have 4 triangles, the total area of the square must be 0.5 times 4, which is 2. And so what we've done is, we can conclude now that the area of the circle must be at least 2. So that's what we now call a lower bound. The way this method is going to work is we are basically going to bound or squeeze in between these two kind of caps, that the area of the circle must be between these two values, and we're going to start to shrink or exhaust those limits. But before we do that, let's consider a square drawn on this time the outside of the circle. And what would be the area of this square? Well, the square would have a side of 2, so the area would simply be 2 by 2, which is 4. And now this forms an upper bound. So what I can conclude is the area of the circle must be no less than 2 and no greater than 4. So the area of the circle must be contained between 2 and 4. And we know pi as being 3.14, etc. And that is indeed between 2 and 4. And now what happens is we're going to now take each of those corners of the square and fold them inwards. And we get a stop sign, or what we know as an octagon. And to find the area of an octagon, we have to use a bit of maths called trigonometry. So if you're not familiar with trigonometry, that's a discipline involved with the study of angles and sides with triangles. And so what we can do is we can find the area of one triangle, and there's a 360-degree angle in a revolution, meaning if we divide it by 8, we would get 45 degrees. And remember, this is still the unit circle, so these sides joining from the center to the edge of the circle are still 1. And we can use another triangle area formula, half AB sine C, in order to find the area, which we will arrive at 2.83. And doing a very similar thing for our now circumscribed square, which is now an octagon on the outside of the circle, we can deduce the area must be 3.31. So again, we started with the bounds of 2 and 4, and those bounds have now been shrunk to 2.83 and 3.31. And essentially, if we continue to do this, we can find that mysterious number pi by bounding our circle and slowly shrinking the area as we increase the sides of our polygon. And so if I drew this and I said, what shape do you think this is? And you might say, oh, well, it's a circle, but in fact, it's a polygon with over 65,000 sides. And so what we've done is we've exhausted the area. Those leftover bits of area are getting so tiny and negligible that they may as well not even exist. And that's what Archimedes was able to find, was that those little bits of leftover area are so negligible, they're so tiny that they may as well be nothing. And so it didn't matter whether it was a circle or a polygon with, tens of thousands of sides, the area was so close that it may as well be simply pi. So he was able to deduce the area of the unit circle is pi. And that's where our formula pi r squared and where the discovery of pi originates from. But something should kind of sit in the back of your mind and say, is that okay? Is it okay for us to say that something that is something that is infinitely small is 0. Is it okay for us to say that the circle and the infinitely sided polygon are the same thing? And that was actually a question that took more relevance later on, and mathematicians tried to tackle this, this new question that came as a result of this, but that will be another video. But it's a very interesting question, and it does have an answer, and we'll look at that in another video. So I hope you enjoyed that. Thank you for watching.